We move on to the next paper. So maybe I didn't say that. In contrast to the original program, the order of presentations has been changed. So this second presentation comes from company Speechly in Finland and University of Helsinki in Finland. It's entitled Fast Text Only Domain Adaptation of RNN-Transducer Prediction Network, and the paper will be presented by Pylkkönen.
Hi everyone, I'm Janne from Speechly. We are a speech technology startup from Finland. And this work about fast text only domain adaptation for RNN models was done with my colleagues Antti, Juho, Samu and Janne. So our motivation for this work was in finding how to efficiently adapt end-to-end speech recognition models to new domains and tasks using only small amounts of textual data. Many of the existing domain adaptation methods for end-to-end systems rely on external language models. And these require changes to the model inference as two sets of scores need to be fused together. And we wanted to find something simpler, a method that would work, as I said, even with a small set of adaptation sentences, and one that would retain the fully neural approach of end-to-end speech recognition. And for this, we turned to look into the prediction network of RNN-Transducer models, which can be interpreted as a language model. If we can fine-tune this prediction network as a language model, we can achieve our goals. So in this presentation, I will walk you through the method we have developed and share the experiment results, which demonstrate that the adaptation method can improve the target domain accuracy by 10 to 45% without compromising the accuracy on out-of-domain utterances. So, as a separate language model is a central concept to our adaptation methods, let's start by looking into the differences between hybrid and end-to-end models. As you all know, the classical hybrid models for ASR consist of separate models for acoustic, language, and pronunciation. And the clear benefit here is that the language model can be trained from a large text corpus, and the adaptation is straightforward as well. However, there are modeling benefits in integrating all of these components into a single network, and this is where the recent success of end-to-end models is rooted. In end-to-end model training, matched speech and transcripts are used, and this limits the amount of language content exposed to the model during training. And because of that, an external language model is often needed in order to maximize the accuracy in a particular task. For this work, we have decided to use a particular type of end-to-end models, namely the recurrent neural network transducer, or RNNT for short. They have demonstrated state-of-the-art performance, especially in streaming applications. And this type of model consists of separate encoder and prediction networks, and the outputs of these two are combined in what is called a joint network. As the input, the encoder network takes the acoustic features, whereas the prediction network introduces recurrency, taking as the input the tokens predicted so far. The joint network is typically just a simple feed-forward network followed by a softmax layer. In our context, the RNNT models are particularly interesting because of the prediction network component, which can be interpreted as a kind of a language model. However, because it does not produce a conditional distribution of the next token given the history, but only a representation to be interpreted by the joint network, it cannot be used as a language model by itself, and this property has instead been used mostly for initializing the network from a neural language model. And moreover, there has been some debate about how important it is for the prediction network to actually process language information, and two examples of such studies are shown on the slide, and those references are of course in the paper as well. As mentioned, often the RNNT models are used together with external language models. But using an external model means that we need to somehow fuse the scores of the language model with those of the network. And for RNNT, several fusion methods have been proposed, but the most widely used appears to be the simplest, the shallow fusion. It simply adds the scores of the external language model to the network scores during decoding. A more traditional way is for using a second language model is rescoring, where the first pass decoding produces multiple hypotheses, and these are then scored with the new language model. But this poses obvious challenges if real-time streaming is required. All of these external language model methods require at least some modifications for the decoding process. A completely different way of adapting for domain adaptation from text-only data is to use text-to-speech generated utterances for fine-tuning the network. This has been reported to work well, but we don't find that method as particularly simple nor as a desirable way for quickly adapting the models. So let's look at our proposal for fast domain adaptation method. The key component to our method is the introduction of a temporary language model output component, which is placed on top of the prediction network. This is depicted on the slide in red and referred here as L. Together with the prediction network P, the language model output L produces a neural language model P plus L, which can be fine-tuned and used as any other language model. The language model output layer L is a simple feed-forward layer followed by a softmax, so it's just like the joint network. Once it is trained on top of the prediction network, the actual adaptation can be performed. And the adaptation is just fine-tuning the neural language model. However, the parameters of the output layer L are kept fixed during this adaptation. For the model inference, the output layer is no longer needed and it can be ignored. The decoding is performed as before with the RNNT, for which the prediction network parameters have been modified during the adaptation process. And although the output layer L is no longer needed at this point, do note that the layer L can and should be reused if multiple adaptation to different domains is needed. So it doesn't need to be trained every time again. Going into details, after the RNNT is fully trained, the language model output layer L is trained on top of the prediction network using the RNNT training transcripts. Prediction network is not modified at this point. Although we have initialized the prediction network from a neural language model, which has been trained from a large text corpus, at this point we are only using the RNNT training transcripts in order to not introduce any mismatch between the prediction network and the LM output layer. For the actual domain adaptation, the parameter freezing is switched. Now only the prediction network parameters are modified, while the parameters of L are kept fixed. So here L acts as a regularizing constraint to enforce that the representation of P remain compatible with the joint network. Additional regularization is used to ensure that the prediction network is not modified in ways which would be harmful for the RNNT accuracy. So keeping the L component fixed is already one way of regularizing the adaptation, but we also added two additional terms in the loss function in addition to the cross-entropy loss. The first is a balancing term, which penalizes the changes in the representations of the prediction network for common utterances. So intuitively, the idea here is that for common utterances, the prediction network should produce similar representations as before the adaptation. So it shouldn't change too much. And this constraint is realized by using the unadapted neural language model induced by the P plus L to randomly generate utterances and then computing Kullback-Leibler divergence between the unadapted and the adapted predictions over those utterances. And this can be viewed as an augmentation of the adaptation loss function with a knowledge distillation loss. Another regularization term is simply the L2 norm of the parameter changes due to the adaptation. The L2 norm on the parameter drift was also used as a stopping criterion for the adaptation. For the experiments, the relative weights of these regularization terms were optimized using a development set. And we observed that the method was not very sensitive to particular values of the weights, so the same values were reused throughout the experiments. Now, a quick overview of the ASR system that we used for the experiments. The RNNT model we used is based on unidirectional layer normalized LSTMs with projection layers. Both the encoder and the prediction network used similar LSTMs with 1,536 memory cells and a projection dimension of 640. The encoder had a single convolutional layer followed by 7 LSTM layers. There were also 2 points of time reduction, so the input frame rate was 10 milliseconds per frame, output was 60 milliseconds. The encoder network was initialized with the CTC loss function. The prediction network consisted of 2 LSTM layers and was initialized by training a neural language model over a 20 gigaword subset of the English Oscar corpus. Joint network was a simple feed-forward network, and its outputs was 1,000 word pieces plus a blank symbol. In total, the model had about 90 million parameters. And this model was trained over 3 publicly available corpora, LibriSpeech, Common Voice, and Tedlium-3, about 2,770 hours. This is not exactly a large amount of data for an end-to-end model, and the results are not state-of-the-art in that sense, but we believe that these results are representative about the gains of the adaptation methods. And anyway, we decided to publish also the results with our production level model, for which the architecture is similar, but it has been trained with much larger amount of training data. So, the results. For adaptation experiments, 2 data sets were used, ATIS-3 and SLURP. The adaptation was done over a dedicated held-out transcript. For ATIS, that is about 6,000 utterances, and for SLURP, 10,700 utterances for adaptation. The adaptation data was therefore rather small. But for a SLURP dataset, there is also a division of utterances into 18 categories. So we decided to use 2 different configurations for this adaptation test. One where all the SLURP data was pulled together for a single adaptation, and another one where each of these 18 scenarios where the utterances were used separately for separate adaptations and evaluated with the corresponding per scenario evaluation data. And this means that the amount of the adaptation data in the per scenario case is only some hundreds of utterances. So the table from the paper shows the main results, the word error rate reductions achieved with the adaptation. Overall, the gains range from 10 to 45% for relative word error rate reduction. And the final level of adaptation for SLURP provides higher improvements. This demonstrates that the method indeed works very well, also with a very small amount of adaptation data. The production model seems to improve even slightly more than the smaller experimental model. Next, we wanted to test the generalization aspects of the proposed adaptation. To evaluate that, we used the RNNT adapted for the ATIS-3 dataset, but tested that with the Tedlium data evaluation utterances, so which after the adaptation represent out-of-domain data. The panel on the left demonstrates that the degradation observed for the out-of-domain utterances is modest and can be made even smaller by increasing the balancing loss regularization weight. The value used for the rest of the experiments was 0.8, and that shows pretty good balance between the in-domain and the out-of-domain accuracies. Now, if we compare these adaptation effects to shallow fusion performance, shown on the right panel, we can see how drastically different the out-of-domain behavior is. In this experiment, a 4-gram language model with absolute discounting was used for shallow fusion. The best results are actually pretty good, even slightly better than with our RNN-T adaptation, but this comes at a severe cost to the out-of-domain accuracy, which degrades very quickly as the shallow fusion weight is increased. And it's worth mentioning that the best performance on all the tests with the ATIS-3 data we obtained by combining the RNN-T adaptation with the shallow fusion. But again, if the generalization aspect is important, then shallow fusion should probably be avoided. To conclude, we have presented a fast text-only domain adaptation method for RNN-T models, which achieve significant accuracy improvements even when very little data from the target domain is available. The adaptation method is simple in a way that it retains the RNN-T architecture and requires no modifications to the model inference. The adaptation method is also practical to the extent that we are using it in our production environment. Compared to shallow fusion, our RNN-T adaptation achieves comparable results, improvements, but with drastically better generalization if out-of-domain utterances are observed after the adaptation. The adaptation method relies on interpreting the RNN-T prediction network as a neural language model, which proves that the prediction network does indeed hold important language model capabilities. There are more details about this aspect in the paper. For example, we noticed that it was important to initialize the prediction network from a neural language model. And that concludes my talk.
Thank you very much. Time for questions, comments. Yes?
Okay, thank you for your talk. So I wanted to know, you mentioned that you could also use TTS to do domain adaptation. And I'm sure that your method is simpler than training a TTS model, but do you think that this is orthogonal? So would you think it's worth to try both, or would you say that your method completely replaces the need to do adaptation by a TTS model?
I would say they are complementary because our method is only modifying the prediction network, whereas with the TTS, you can at least change also the joint network and maybe even the last layers of the encoder. But we actually tried some of that, and it seemed like the TTS adaptation, not only being a bit more complex, was more sensitive to the particular data sets. So it was harder to make that generalized, like in a general environment.
Okay, thank you.
More questions, comments? Maybe I can ask a question about your concept. I mean, what you're doing, if I understand correctly, could also be used for the integration of a big external language model. Would that be better than the standard methods that we have nowadays? What do you think?
Do you mean large neural language model?
Yeah.
In a way? I mean, that's basically what we think that the RNN-T is doing, in a way, that we initialize it from a neural language model.
But then why do you use the term adaptation? Then you could say it's just integration. It's one way of integrating an external language model.
So during the RNN-T training, then the prediction network kind of drifts away from the neural language model, and now our method is kind of bringing it back to the...
You are saying you have to repeat the acoustic training for this specific language model.
Well, the RNN-T training is modifying the prediction network. I don't think that it would work very well if we would freeze the prediction network parameters during the RNN-T model. So after the RNN-T training, you don't have the same neural language model anymore. And we are kind of trying to bring it back or closer to the language model functionality.
Okay. More questions, comments? Maybe a question of the chat channel? There's some question about your regularization. How critical is that?
Sorry, about?
Regularization loss.
Okay.
How important is that?
So one example is here that we see that at least for the out-of-domain accuracy, it clearly improves when we add the balancing loss weight. But otherwise, I would say it was maybe more important for us to be sure that this method works well with almost any input data, because that's how our production system kind of works, that we don't have a good control on the input of the adaptation. So the regularizations help this to work in a very wide variety of applications. But it wasn't, I would say it wasn't absolutely necessary, but definitely it helps in the generalization.
Okay, I think we have to stop here. So thank you very much again.